Hello guys, welcome back to my channel, and in today's video I'll be going through the May June 2024 paper for IGCSE Physics variant 43. So in the past few weeks I've gone through variant 41 and 42, so make sure to check them out if you haven't. So for today I'm going to be going through variant 43. So let's start. A ball of mass 130 grams is launched from the ground at an initial velocity of 14 meters per second vertically upwards. It decelerates until it's at rest momentarily at a height h above the ground. Okay. Define deceleration. So one of the ways we can define deceleration, we can say it's it's like negative acceleration, but then since it's 2 mark, we should also define what acceleration is. So we can say it's negative, and acceleration is rate of change of velocity, so we can say negative rate of change in velocity. So this is acceleration, and this negative shows that it's deceleration, so it's negative acceleration. The acceleration of free fall is 9.8. Show that the time taken for the ball to reach height h is 1.4 seconds. Ignore the effect of air resistance. All right. So let's look at the acceleration formula. So that is, acceleration is change in velocity over time. So we can rearrange this formula to make time the subject. So it would be time equals change in velocity over acceleration. So now we have the values. So as mentioned in the question, velocity is 14. So we can say 14 over 9.8. So 14 over 9.8 gives us 1.42. So this is the same as this one, just rounded to the two significant figures. Part C, calculate H. Ignore the effect of air resistance. So whenever we ignore effect of air resistance, acceleration is constant, so it's okay. So when we ignore air resistance, that means there is no changing acceleration. So what we can do is, we should know that there would be no energy wasted because there's no air resistance, or at least we're ignoring it. So that means as it's falling, or as it's going vertically upwards, so the ball is first, it was at here, and then it goes upwards. So as it's falling, it's going upwards. At the top, it has the GPE, or the gravitational potential energy, and at the bottom, it has kinetic energy since it's moving. So since there's no air resistance, all the kinetic energy is changed into gravitational potential energy. So we can say kinetic energy equals GPE. So formula for kinetic energy, that's half mv squared. GPE is mass times gravity times height. All right. So we're told to find height. So the mass, we can just cancel them. Gravity, we know that's 9.8. So it's half times. Velocity is, of course, 14. 14 squared equals 9.8 times height. So 14 squared divided by 2, that's 98. So 98 equals 9.8 times height. So divide both sides by 9.8. We get a height of 10 meters. And there's the 3 marks. The ball is dropped from the top of a tall building, so we know that it's free fall. Describe and explain the motion of the ball as it falls. Consider the effect of air resistance. So this time there is air resistance. Okay, good to know. So what happens at first is the ball increases its speed or accelerates. So at first, the ball accelerates. Then, as speed increases, air resistance also increases. Also increases. So, since the air resistance increases, the resultant force decreases. Force decreases. So once the resultant force is decreased, so as speed increases, air resistance also increases. So it gets to a point where the downward force and upward force, they match each other. So when that happens, resultant force becomes zero and acceleration becomes zero and the object reaches terminal velocity. Object reaches terminal velocity. So let me clarify it again. So firstly, what happens is as the ball goes down, the speed increases, and while the speed is increasing, air resistance, which is acting opposite resistance, also increases. So at some point, the the downward force is usually the weight because it's free falling. So weight becomes equals to the air resistance. So when weight is equals to air resistance, resultant force becomes zero. So that means acceleration also becomes zero and the object reaches terminal velocity or a constant velocity. Hope that's clear. Question number 2. Figure 2.1 shows solar powered traffic's warning lights. Okay, the energy from the solar light is stored in a battery. Name the energy stored in a battery. That's chemical energy. Chemical energy. B. The two lights, figure 2.1, are connected in parallel. Okay. State one advantage of a parallel connection in a lighting circuit. So whenever they're connected in parallel, if one lamp breaks or stops working, if one lamp stops working, the other still works. But if this were connected in series, if one lamp stops working, both of them stop working. Part C. Efficiency of a solar cell is 22%. The power supplied to the light is 15 watts. Okay, state what is meant by 22% efficiency. So 20% efficiency means like the useful energy is 22% of the total energy. That's what it means. So in this case, we have 15 watts. So the useful energy is only 22% of that 15 watts. So part 2 states calculate the solar power input of the solar cell. Okay, so 15 watt is the power supplied to the light. So this is 15 watt is the useful energy. So that means 22% is the 15 watt, which is a useful energy. So what is 100%? Equal to, you can say x. So cross multiply, we have 22x equals 100 times 15. That's 1500 over 22. So 1500 over 22 gives us 68.2 watts. So this is the total amount of energy generated. State 2 advantages of using solar cell to power the traffic warning lights compared to using mains electricity. Okay, so the mains electricity is like electricity generated from a transformer or from a distance place. So the first one is this one, the solar panel one, it's not affected by power cuts because it works from a solar panel. So as long as there's sun and as long as energy stored in the battery, it works. The second one is there's no need for long cables because usually when it's connected to a main supply, mains electricity, what happens is there's a long cable going from the source all the way to the lamp. So there's no need for that since we're just using the solar panel. Question number 3. Figure 3.1 shows two children balanced on a seesaw. A seesaw is a length of a wood which rotates about a central pivot. Okay. Child B moves 0.05 meters away from the pivot. So, okay. Calculate why the seesaw rotates clockwise. So what happens is this child moves to this side. So what happens is the clockwise moment has increased. So when the child moves back, there's going to be a clockwise moment. So of course the seesaw is going to be going clockwise. Part 2. Child A puts on a backpack and the seesaw is now balanced. Alright, calculate the mass of the backpack. Okay, so what they're testing on is the conservation of moment. So what that states is when the moment, the anti-clockwise moment, so the moment of child A is equals to the moment of child B. So for that to happen, we know that moment is force times distance. So the moment, first we have to calculate the moment for child B. So to do that, the distance is 0.8, but then they told us it moved 0.05 backwards. So it's going to be 0.85 times 900 newtons. So this moment should be equals to child A's moment. So child A's moment, it's 450 plus the backpacks, the weight of the backpack times 1.6. So this gives us 765 equals, so distributing 1.6 gives us 720 plus 1.6b. So we can subtract 720 from both sides. We get 45 equals 1.6b. So dividing both sides by 1.6, that gives us the weight of the backpack, which is 28.1 newtons. But then as you can see, they asked for the mass. So to find the mass, we do 28.1 dividing by the acceleration, which is 9.8. So that should give us 2.9 kilograms, rounded to two significant figures. Part B. The concrete floor under the seesaw is replaced with a rubber floor. The child falls from the seesaw and experiences an impulse when they hit the floor. Define impulse. So impulse is force times time. Simple as that. Part 2. Explain how the rubber floor reduces injury to the child. Use ideas about impulse, force, momentum, and time in your answer. So compared to the rubber floor and the what was it again? The concrete floor, yeah. Compared to the rubber floor and the concrete floor, what happens is the impulse is the same for both floors. The value of the impulse is the same, But for the rubber floor, it extends over a longer time. Over a longer time. So we know that force equals the change in momentum over time. So since force is changing momentum over time and the time is larger for the rubber floor, if the time increases, the force decreases. So that means there is less force on the child. That's the answer. Let's go to question number 4. Figure 4.1 shows a stainless steel saucepan being heated on an electric cooker. The saucepan contains water. State what happens to the water particles as the water temperature increases. So the water particle, they move faster. So when the temperature increases, their kinetic energy also increases, so they're going to start moving faster. The saucepan contains 250 centimeter cubes of water. Specific capacity of water is 4,200. Density of water is 1,000. Show that the mass of the water of the saucepan is 0.25 kgs. So they've given us volume and density. So we know that density equals mass over volume. Rearranging this, we get mass equals density times volume. So density, that's 1000, and the volume is 250 centimeters cubed. Since it's in centimeter cubed, we have to convert to meters cubed. So what we do is we divide by 1 million, or 10 to the power of 6. So it's going to be 1000 times 250 times 10 to the power of 6. So that would give us 0.25 kgs. So that's the mass. Part 2. Calculate the energy required to increase the water temperature from 20 to 65, right? So we use the formula for specific heat capacity, which is Q is equal to MC change in T. So Q, that's the energy, and the mass, it's 0.25, and specific capacity, or C, that's given to us, which is 4,200. Now the change in temperature, so 65 minus 20, that would give us 45 degrees Celsius. So whenever we can just multiply this, so 0.25 times 4,200 times 45. That gives us 47,250. And then energy is of course in joules. That's our answer. Part 3. The heater supplies enough power to heat the water in 39 seconds. A student measures the time taken to heat the water as 115 seconds. Suggest why the actual time taken to heat the water is longer. Assume that a student takes accurate measurements. So what happens is it's heat energy. So heat energy can be dissipated. It can transfer to the maybe like the pan, or the heat energy can transfer to the saucepan. So we can say thermal energy could transfer to the saucepan. So according to the student's calculation, 39 seconds is if all the thermal energy is transferred to the water. But then, since some of the energy is transferred to the saucepan, that means heat energy escapes to the surrounding, so it would take longer time. Stainless steel saucepan is replaced with an aluminum saucepan of the same mass It contains the same volume of water. Specific heat capacity of stainless steel is 500, but specific heat capacity of aluminum is 890. Explain how using aluminum saucepan will affect the time taken to heat the water. So to answer this, because aluminum has higher specific heat capacity, more energy is needed to increase the temperature. So since more energy is needed, that means it takes longer time to heat the water. So basically what I'm saying is that aluminum has a higher heat capacity. So when you talk about specific capacity, is the amount of energy required to raise the mass of 1 kg by 1 degree Celsius. So to raise 1 kg by 1 degree Celsius. So the higher the heat capacity, that means it would require more energy to raise the temperature. And since aluminum has the higher one, it would take longer time. Question number 5. Figure 5.1 shows two containers, each filled with hot water. The outer surface of the metal container is hot. Explain how electrons transfer thermal energy through the metal container, through the metal of the container. So firstly, what we have to understand is that the metal has delocalized electrons. So what we mean by that is it has free moving electrons, delocalized electrons. So they gain energy. And after they gain energy, since they're free to move everywhere, the electrons move through the metal. Then they will collide with the other particles. And then that way they transfer heat energy. Part B. The outer surface of the non-metal container is much cooler than the outer surface of the metal container. Explain why non-metal conduct thermal energy less well than a metal. So it's kind of similar to the first question. Non-metals have no delocalized electrons. That's the answer. Part C. Explain in terms of particles why gases are poor thermal conductors compared to non-metal solids. So in gases, okay, let's compare. So this could be like the particles in non-metal solids, very close to each other. But in gases, the particles are very far apart from each other. So what that means is, so particles are far apart from each other. So what happens is there is fewer collisions between particles. So there is less transfer of energy due to the fewer collisions. Part 6. Figure 6.1 shows a thin converging lens used to produce a magnified image of an object AB. Alright. A. Explain the meaning of the terms principal focus and the focal length. So the principal focus is also known as the focal point, and it's the point where the light rays converge towards to after passing through the lens, through the lens. And the focal length is the distance between the lens and the focal point or the principal focus. So this, for example, in this image, this is the focal length. Part B. On figure 6.1, draw a magnified image of AB. Show your working. So it's 4 marks. So we really have to be detailed here. So AB, we have this upward facing arrow. So now we have to magnify it. So they told us to show our working. So first we have to draw the ray lines. The first one we could draw is passing through the center of the lens. Wait, let me redraw that. Okay, passing through the center of the lens. And the second one is first horizontal until the center of the lens and goes through the focal point or F2. So if we continue these lines, we can see that they'll never meet. So whenever they do meet, what we do is we continue the lines using virtual rays on the other side. So we have virtual rays. So they meet somewhere around here. So the dotted lines means that the rays are virtual. So where they meet is where the image is formed. So this is the magnified image of AB. Question number 7. Figure 7.1 shows two charged metal plates. X marks the position of the center of the space between the plates. Okay. Figure 7.1, draw at least 4 field lines to show the pattern and direction of electric field between the two charged plates. So field lines. So we just have to draw straight lines. At least 4 lines, so we can just draw this 4. And nextly, they told us field lines. So whenever it's field lines, we consider the direction of the positive charge. So the positive charge, it would move towards the negative charge because it's attracted to the negative charge. So the arrow should point to the negative one. But if this was also a positive charge, the field lines would be away from the positive charge because they repel each other. Part 2. Describe the effect of a negatively charged particle placed at X. Okay. So it would be attracted towards the positive side or towards the top. Towards the positive side. So it would go up. During a thunderstorm, an electric field is set up between a cloud and the ground. The charges on the cloud and on the ground are shown. So on the cloud, negative charge. On the ground, it's positive charge. Lightning. The lightning shown in figure 7.2 discharges a current of 28,000 amps for 0.012 seconds. Calculate the charge that flows from the cloud to the ground. Okay. So we know that current equals the charge over time. So rearranging this, charge equals IT. So it's going to be 28,000 times 0.0012. That should give us 33.6, and it's coulombs. That's the unit for charge. Part 2. The lightning transfers 1.2 times 10 to the power of 8 joules of energy. Calculate the potential difference between the base of the cloud and the ground. So we know that potential difference is the energy transferred over the charge. So the charge is 33.6, energy is 1.2 times 10 to the power of 8. So 1.2 times 10 to the power of 8 divided by 33.6, that gives us 3.57 million. So we can just write that as 3.57 times 10 to the power of 6. And potential difference is always in volts. Question number 8. All right. The image, figure 8.1 shows images produced during two different medical scanning procedures. Ultrasound scan of a fetus and X-ray scan of a hand. A, part 1. Define ultrasound. So that's just a sound with frequency greater than 20,000 hertz or 20k hertz or 20 kilohertz. So a sound with frequency greater than 20,000 hertz. State how the speed of sound in liquid compares to speed of sound in air. So sound is faster in liquid. This is because the particles are closer in liquid than gases, so the sound could transfer easily by the collisions of the particles. X-rays are part of the electromagnetic spectrum. State the speed of X-rays in a vacuum. So electromagnetic spectrum, each part of the spectrum, they have a speed of 3 times 10 to the power of 8 meters per second in a vacuum. So this is the speed of light. So they all travel at the speed of light in a vacuum. So they all have the same speed. Describe 3 similarities or differences between the use of ultrasound and X-rays in medical scanning procedures. So let's go for similarities. They both show internal body parts. And the next one, they could both travel through the body. So for the last one, we can do a difference. The difference is that X-ray could be harmful because it can expose to radiation. That's why, like as seen earlier, ultrasound is used to scan for a fetus, because if we used X-ray, the fetus can be exposed to radiation and the tissues and the cells, they might mutate. Question 9. Figure 9.1 shows a mobile phone being charged on a wireless charging plate. When a charging plate is switched on, there's an alternating current in the primary coil and a secondary coil is in the mobile phone. Explain how a current is produced in the secondary coil. So, to know how the current is produced in a secondary coil, it's the same phenomenon as the transformer. So what happens is, let me just draw a transformer to explain it first. So we have the primary coil. So alternating current goes to the primary coil, which induces an alternating magnetic field throughout the iron core. So when over here, the secondary coil would cut the magnetic field. So that would induce an alternating current in the secondary coil. So we can say alternating current is produced, alternating magnetic field actually. Magnetic field is produced in the primary coil, and it's cut, or the magnetic field is cut by the secondary coil, which causes alternating current, or AC, to be induced in the secondary coil. So that's the answer for the 3 marks, but I don't know why they made the space so small. Part B, maximum energy stored in the battery of the mobile phone is 0.012 kilowatts. Show that this maximum energy is 4.3 times 10 to the power 4 joules. Okay, so it's kilowatt hour. Okay, so what I have to do first is convert this to watts. So 0.012 times 1000 to change it to watt hour. So that would just give us 12. So 12 watt hour. Now we have to convert this hour to seconds. So it's going to be 12 times 3600 seconds. So that would just give us 4.3 times 10 to the power 4. Part 2. The charging plate in Fig 9.1 has a useful output of 15 watts. The phone manufacturer claims that the battery can be charged to 15% capacity in less than 30 minutes. Okay, show that this claim is true. So to calculate power, it's energy over time, because it's the energy transferred per unit time. So energy. So now we have to find the energy. So energy is power times time. So we know that energy is 15. The power is 15 times the time. So let's check how much it charges in 30 minutes. So in 30 minutes, which we also have to convert to seconds by multiplying by 60. So the energy transferred in 60 minutes, in 30 minutes, it's 27,000 joules of energy is transferred in 30 minutes. So in percentage form, the total amount it can transfer is 4.3 times 10 to the power 4. Or we can just rewrite it as 43,000 joules. That's the maximum energy. So now we just have to find the percentage. So 27,000 over 43,000 times 100. So that would give us 63% approximately. So in 30 minutes, it has charged to 63%, and 63% is greater than 50%. So yeah, the claim is true. It can charge over 50% in 30 minutes. Question number 10. Leaks in underground water pipes are detected using radioactive tracers. Figure 10.1 shows a radiation detector above the water pipe. Okay, so we have a radiation detector above the water pipe. Before the radioactive tracer is added to the water, the detector measures the background radiation above the pipe. The average background radiation is 26 counts per minute. Define background radiation. So it's the radiation that always present in the environment. So it's a radiation that's always there. Suggest one source of radiation that may make a significant contribution to the background count rate. So there are different sources of radiation. So we can say that it's radon gas. We could also say cosmic rays coming from the sun. And we can also mention other sources of radiation that contribute to background radiation. A radioactive tracer is added to the water. The counter in figure 10.1 shows the count rate in counts per minute above the leak of the water pipe. Determine the count rate due to the tracer. So it's 382 as shown in the diagram over here. That's the total count rate, but we also have the background radiation, which is 26. So we just have to subtract. So 382 minus 26, that would give us 256 counts per minute. Part B. Suggest which radioactive emission, alpha, beta, or gamma, is suitable for detecting the leak in water pipe. Explain your answer. So that should be the gamma ray. I'll explain in a minute. So the gamma ray is the one with the highest penetration. So because of that, the alpha and beta would be stopped. Stopped before reaching the detector. But gamma has higher penetration. So it will not be stopped. That should be the answer. Part C. Explain why the radioactive isotope must not have a very short half-life. So if it has a very short half-life, that means it won't allow enough time to be detected. So a very short half-life will not allow enough time for detection before it decays. Because if it has a very short half-life, that means it would decay continuously, or it would decay in short amounts of time, so it won't be detected easily. Explain why the radioactive isotope must not have a very long half-life. So if it has a very long half-life, that means it would contaminate the water supply. So contaminate, it will contaminate the water supply. That's our answer. A galaxy is approximately 1.2 times 10 to the power of 26 meters from Earth. Scientists observe light from a distant galaxy. The wavelength of the other light is longer than wavelengths of light emitted from the galaxy. State the name of this effect. It's called redshift. Part B. State the current estimate for the Hubble's constant. So you should know this. It's 2.2 times 10 to the power of minus 18 per second, or second to the power of minus 1. So the formula for Hubble's constant, I'll get to that later. Calculate the speed at which the galaxy is moving away from the Earth. So this is when we would use the Hubble's constant. So the formula for Hubble's constant is velocity over distance. So we can rearrange the formula to find the speed, so which is Hubble's constant times the distance. So it's 2.2 times 10 to the power of minus 18 times 1.2 times 10 to the power of 26. So when calculating this, we would get 2.64 times 10 to the power of 8. Of course, meters per second. Scientists have measured the speed at which distant galaxies are moving away from the Earth and their distances from the Earth. The measurement suggests that all the universe was at a single point. Explain why. Okay, so what we can say is the universe is expanding. So if the universe is expanding and the planets and the galaxies are moving away from each other, that means, okay, meaning, we can say meaning, so if the planets are moving away from each other, that means in the past they were close to each other. So meaning in the past, the galaxies were closer to each other. So that was the last question. If you have enjoyed this video, make sure to like and subscribe. And I know the October-November exam is coming up soon, so for my next video, I'll be making my prediction for the October-November paper 4. So make sure to stay tuned for that and make sure to subscribe so you won't miss out on that video. And thank you for watching.